Well, we're going to continue to have folks come in and get their seats, but I like to keep everything on time. And, of course, there's never enough time. The entirety of Cisco Live is built up around having all these amazing technologies, and there's just not enough time to learn it all. I myself have been with Cisco since 1999, back in the 1900s, so that gives you an idea. And that was actually why I came up with this session. For the record, I assume everyone has read the abstract and knows why they're here. Anyone not know why they're here, or came to the wrong session, I guess? Okay. But the fact is, we spend so much time telling you about this amazing new feature widget thing we have. Quite often we forget about the very basics, the fundamentals of how networks are built. So, talking about it with various engineers, I said, you know what, we actually need a session that goes back to the very basics, okay? So for some of you, this may actually seem very remedial, very simple. It is meant to be simple, okay? What we're gonna talk about, and in particular, for the title, is campus networks and campus wired, right? So if I can understand the physical design of the network, then I start to layer things on top of it. This is how I put wireless on top of it. This is how I apply security. This is how I apply quality of service. But again, really understanding the physical design of the network, then how do I put wireless and those kind of things. So that's the main goal of this particular session. And I need to turn on my clicker. All right. There we go. And of course, it clicks twice, right? So I'm a big believer in the agenda. Again, this session is meant to be the basics. My style is I do not like to read slides to people. With a show of hands, who here does not know how to read? Anybody not know how to read? Perfect, okay, we're off to a good start. So my job is not to read to you. Everybody here can do that. And also, if you can get the slides, if you go into your Cisco events, you can actually see all the slides. I also have a bunch of hidden slides. So there's even more content than what I'm going to present to you. But my point is, you can always go back and read the slides, right? You don't need me to read the slide to you. But my goal is to explain why it's important to you. Again, the very fundamentals. Yes, I know there's some cables, and I know there's some layer 2 and some layer 3. That's fine. What's important about this particular piece? And so that's why I like to sit on the agenda for a few minutes. The first one is, what is a campus network? Now again, very basic. It seems simple. We use this word all the time, right? Who here considers themselves sort of like a data center networking engineer? That's your primary concern. And don't be shy. I mean, the reason I'm making this point is, we all come from a certain background, right? And you're naturally going to take your experience and build your network with your experience, right? But a data center is built in a certain way, right? And so, yes, we use this word campus a lot, but we don't often think about what the campus is trying to do. So it's important just to talk about what is a campus. Then we'll talk about, classic multi-layer network design. What's a 1-tier? What's a 2-tier? 3-tier? When is it appropriate to make it a 4-tier? You keep going, a 10-tier, it doesn't matter, right? But it's understanding what each of those layers do. And again, with that basic concept of this is, what's going to make my network operate in a certain way. And there's variations to all these rules. That's why I used the data center example. There are variations to all these rules, but understanding why I build this particular layer for the campus network and be able to use that in your network designs. We will actually spend most of our time in that second part, because then it's just layering things on top. Now I understand why these layers are there. Okay, now how do I want to connect these layers together? So things like equal cost multipath, stackwise virtual, and virtual switches. And this is like a comparison. So the other part of this is I'm going to talk in pros and cons. I'm not going to tell you this is the right thing. You should absolutely use this new technology. I'm just going to tell you it works this way, you can do it with this technology, you can do it with that technology, but remembering why it behaves that way in the campus, okay? Now, once I've connected all of these layers, then I'll be talking about some sort of a fabric type protocol, right? We use words like overlay. Oh, and the other point is, there are sessions on all of these. They're the deep dive, the longer version of each of these, right? So there's entire sessions on MPLS, entire sessions on EVPN and software-defined access. But again, I'm going to explain it from the perspective of, here's the topology, you've connected up the physical links this way. If I try it with MPLS, this is what's going to happen. If I try it with EVPN, this is what's going to happen. And how do I compare those two? You know, you're all network designers. You're going to have to go back and explain to your boss, hey, I think I need this new technology. And you need to be able to explain to that boss, how is it going to make my network a little bit better, right? And then last but not least, again, there are entire sessions on wireless and security. So it's not that. It's just things about wireless and things about security that you need to apply to your campus network as you're designing the wired, the physical switching and routing network, okay? All right. So what is a campus? Talked about that. I will use this term place in the network. You'll hear various people talk about it, or they'll just say pin. But it just means like a role, a job, and a specific layer in the network, and what's the job that that pin is doing. Which gets us to this concept of multi-layer model. Anyone that's been here for like over, say, 10 years, 20 years? Okay. I also wanted to know who was like the old timers and who was new. We used to actually call it the multi-layer model. So I just threw that in there to kind of, and you know, again, the distribution or the separation of responsibilities and those kind of things. Very briefly, I'll talk about chassis and specifically modular versus fixed, right? So this is another one of those basic decision criteria. It's largely religious, philosophical, pros and cons. So I can tell you why you might choose a modular design or why you might choose a fixed design. But these are going to be critical decisions when you're designing, okay? Talk very briefly about cabling, same sort of thing. It's not a full session on how cabling works, but your cabling decisions will affect your network design, okay? And then lastly, mixed in with all of this, the features that are happening at each layer, at each pin. So I like to start with the dictionary definition. Again, I'm not going to read the slides to you. That's not my job. My job is just to point out certain things, right? So it says a group of one or more buildings and the surrounding grounds where people and their belongings work together, right? So the only thing I really, really want you to take from this slide is people, us, right? And of course our devices, our laptop, our phone, these types of things, right? And this is, again, why I asked sort of the data center question, because if you put your mind in that way, I'm a human, I'm coming into work, I'm plugging in my laptop, those are the types of things that I have to account for when I'm designing. They do tend to be in a similar geographic area. Why is this important? We use words like LAN, we talk about metropolitan area, but the point is that they're all located in the same, and I use these drawings on purpose. It's like a university or it's a hospital, right? And those kind of things. And again, the access piece. So my job is really just to connect that person and his machines to the rest of the network, right? So this is a picture, a photograph of the Cisco San Jose, California campus. Cool, whatever, that's not the point. What I'm trying to show you is all of these different buildings. And again, it's just to kind of reinforce this idea that, you know, it's a geographic area. So if you think about it, and the multiple floors in the building. So people are coming into work, they're going up to floor number 4, you know, and they need to connect between the different buildings. So this is going to affect, again, your, how does the fiber optics work? You know, how long is that fiber optic? So what kind of transceivers do I need? How many ports am I going to need? Those kind of questions, right? So again, it's really the title says everything. When you hear the word campus, think of geography. Think of the physical layout of the building, even here in the Amsterdam RAI building, right? So the other part of that then, as I was getting on, was the cabling. And the physical infrastructure of the building. So, and I have a cabling section. So I'll talk about this again down there, but the point is, oftentimes, this is set when the building is constructed, right? They will put the actual wires in the wall, and it's up through the ceiling and these kind of things. So understanding how many cables do I have, what is the quality of that cable, it goes up and it goes across. We say 100 meters is the distance of the cable, but can you define how 100 meters goes up through the ceiling, comes back down the wall, and then, it may only be 10 meters away, but it's 100 meters inside the wall, and those sorts of things, okay? And I'll also talk about this, trying not to read slides, but key points. You'll hear acronyms like MDF, IDF, BDF. The important word there is distribution, okay? It's a framework. It stands for main, MDF is main distribution framework, but it is a hierarchical model starting from a core, right? So why do we have these words, and what do these words mean, and how do they affect my design? And then you'll hear words like wiring closets, right? And it's an actual closet, and that's where I need to then distribute the fiber down to those things. So again, sounds very basic, but the point I'm trying to drive home is thinking about how it is in the wall and how is that going to affect my design, okay? So I was asking the question about data center to set up this joke. Campus is not data center, okay? Yes, they are 80, 90, 95% the same. There's layer 2, there's layer 3, I have host, MAC addresses, routes, fine, but the physical geography of how I set up a data center is very different than how I set up the network in a campus. Okay, particularly like number of layers, why do I have that layer? It's very common to see a 2-tier spine leaf in a data center. Campus tends to be a 3-tier, okay? So yes, you can apply certain data center logic to a campus, but you'll start to run into problems, okay? That's a real campus network. Anybody have this wiring closet? That's about everybody? Okay. So you get the point. A picture is worth 1,000 words. The one I do like to point out is this little compact switch. And this is, some environments, it's actually in the wall, or it's enclosed. There's sessions on smart buildings and these things. If you think about it, I literally put a switch in the wall, and it's not about connecting to my cool Cisco IP phone. It's about a heart monitor or some room sensor. So things like that. Okay. So I talked about the pins. Most of the session is a topology diagram, okay? But it's to reinforce which protocols are running there, why are those protocols running there, and again, the separation of responsibility. So, and I'm going to talk about each one of these. So everybody sort of knows the classic 3-tier core distribution access, okay? That will be your basic template for every single design. What people do not often think about is a 4th tier, okay? It's about the number of ports I have, the number of routes that I have, and scale, right? So at a certain point, it now makes sense to me to introduce an additional layer that just interconnects all of these smaller areas, right? Similarly, I can expand my access layer. We're going to talk about each one of these, by the way. I have a slide on every single one of these. The access layer is truly where I'm connecting to that person, to his device, an IP phone, a camera, a wireless access point. But depending on what I do as a business, we have industrial areas, they're very, very long distance. So you may have additional layers of just access. I just need to spread out this access further and further. And in practical terms, then it's okay, let's talk about layer 2 switching. Let's talk about spanning tree and loop prevention. How quickly does it converge, and why does it converge that way, and so on. And then over on the far side, you can see this other term, collapsed core. And we're going to talk about this as well. But I left it on this drawing on purpose, right? There's the other direction, which is I want to now start to shrink things, right? The scale is not high enough. does not make sense to buy another expensive Cisco device, right? I mean, our stuff is real cheap, and I know you guys love spending money. And you know, I said this in the beginning, like, my goal is to try and help you with your design. Why do I buy this box? So I want you to buy the boxes, but I want you to buy the correct box. So there are certain designs based on scale that I will choose to collapse layers, right? This also gets in trouble because my boss is really cheap, and he tells me, do you need that particular switch? You know, and that's fine for now, but then like 1 year from now, we suddenly start having MAC address scale problems, or the routing table is exhausted. It's like, I told you 1 year ago, we probably should have got that other switch, but you insisted we do this collapsed core design, okay? All right, this is a busy slide. I don't want to read everything to you. What I wanted to show was just, and by the way, I should have said this in the beginning, I come from the campus networking world, which is traditionally catalyst switching. So I am catalyst biased. Somebody already like leaned over and is like, what if I put a Nexus switch there? So it isn't meant to be religious. My message is whether it's a Nexus switch or catalyst, it's really more about, again, scale, MAC address scale, routing scale, port density, those sorts of things, okay? But my goal on this slide was to show you what I was just saying. Yes, I can make a Catalyst 9300, which is actually like an access switch, run it as a core. Who has a 9300 as a core? It's actually a small number. Like, don't be shy, I'm asking a serious question. It's just a scale and port density question. And I explained to my engineering, and I work very closely with engineering, that yes, 9300 is a core box, and let's call it a core box. And similarly, I can put multiple layers of so-called core switches together, and those sorts of things. So, but from a design perspective, you always still have this separation of responsibilities. So this is back to what I was saying in the beginning. As long as you remember what a core does, then it doesn't matter if it's a 9300 or 9500, 9500, 9300, and so on. And if you'll notice the little guy in the corner, he says, just remember, remember it's the cheap boss that's making you buy the 9300, building a two-tier network, and not planning for 3 years, 5 years into the future. If you try to collapse all those layers, that means that collapsed box has to have the scale and the port density for the next 3 or 5 years, okay? Okay, modular versus fixed. Again, I said I'm not religious. I'm not going to try to convince you one way or the other. My personality is pros and cons. The right tool for the right job, okay? Both of these are perfectly acceptable. And when I say philosophy, it's about operations and how often do I need to change this environment. So modular is a box, a chassis. You stick it in there, and you change the modules as your port speeds change, right? Maybe we're using 10 gig today. I'm looking at 25 gig or 100 gig tomorrow. Take out the module, put in a new module, right? Conversely, I can go with a fixed design, but if I change from that 10 gig design today, I need to pull out that entire switch and put in a new switch to do it, okay? So it just sort of lists off that way. Modular tends to be more flexible, but it's more complex. There's a bunch of moving pieces that can break. You'll see, I use some acronyms in here. MTBF, mean time between failure. COGS is cost of goods. In other words, it's more expensive, it can break more easily because there's more moving pieces, right? A fixed box is just a chunk of metal, so it has much higher MTBF, less things can change. So there's a lot of good reasons to also prefer a fixed design. Just remember that, if I want to change the ports, I'm ripping out that box, okay? All right, cables. So this is a busy slide, I know. What I wanted to do, in one spot was just kind of draw your attention to things like distance and cable quality, okay? And this is true for copper cabling as well as for fiber cabling. Obviously, when we talk about the access layer connecting to people, it tends to be copper. Easy, right? If you are building a brand new building, you probably should put in category 6A or even category 7. Is anybody actually deployed Cat 6A? I'm curious. So it's actually a good number. I know it's more common in Europe. But a lot of you did not raise your hand, meaning that your network is still running Cat 5A, 5E. So these get into the distance of the cable and the bandwidth that it can support, right? So you go into some of these other sessions, they'll be talking about multi-gigabit Ethernet, 10G base T, 10 gig copper, and so on, right? So again, just design decisions about the cabling that I have. The other interesting thing on the right, this is all fiber, but it's divided into SFP-based, or the two-pair LC fiber, right, versus this newer QSFP. Now, the other thing that's interesting is just looking at the connectors themselves. This is not a full session on cabling, but the QSFP originally started as a patch panel cable. So this MPO, MTP type of cabling. And if you look at the picture, it's a lot of little lights, it's a lot of cables bundled together. So it's sometimes called a trunking cable. And it was for patch panels, right? And that's amazing for a data center. So one of the other things I used to talk about data center is the distance. Remember I told a story about geography and the cables are in the wall. When I'm in a data center, they're like 1 meter away. I can just disconnect the cable from rack to rack and boom, suddenly I'm at 100 gig. You can't do that in the campus because the fiber that's in the wall or across the street is already there, right? So majority of networks in campus tend to be this SFP-based two-pair LC, right? So for that reason, you should be looking at, and particularly from like the access layer to the distribution or distribution to core, you should be looking at SFP options. So if you go to some of those sessions, they'll be talking about 25 gig now, 50 gig. By the way, we're now launching 50 gig Ethernet on SFP. So that's like a buzzword to ask about is SFP 56. But you get the point, right? Cabling is very important to you. Again, the switch that you choose, the type of line card that you choose is going to be directly affected by this decision, okay? All right, it's skipped ahead. Again, I'm not going to try and read every single thing to you. The point of this slide is really just to show you kind of like layer by layer that you'll have these variety of different protocols running. This is unicast focused, right? The other thing to draw attention to, the most important thing, and we'll get onto the individual devices in a moment, but there tends to be in a traditional multi-layer design, layer 2 from the access layer to the distribution layer. And then from the distribution layer, it tends to be layer 3 routed to the core, okay? I should also say there are exceptions to all of these rules, okay? You could do layer 2 all the way up. There's even an option to do layer 3 all the way down to the access layer, okay? But as long as you remember the basic rules, it all makes sense, right? So all the little words I didn't want to read off on the side, it just depends on which role, okay? And again, scale. So you're looking at a switch, you're looking at these stupid data sheets that Cisco makes. You're looking at like number of MAC addresses, you're looking at number of routes, number of access control lists, right? And those sort of things. And you're like, this is going to be a core box, so I need to have a certain routing scale for this to do it, okay? Or it's a pure access layer switch. Maybe I don't need a lot of routes, okay? And then in another life, I'm a multicast person. So anybody here like using a significant amount of multicast, like as a part of your business? Okay, it's a fair amount, okay. Anyway, the same rules apply, right? If you're in an L2 switching environment, you're dealing with things like IGMP, MLD, but it's a layer 2 context. It's broadcast, link local multicast. And then in the core, it tends to be routed. That's where you're putting your rendezvous points, MSDP, these types of things, okay? And when you're looking at those stupid data sheets, those are the keywords you're looking for. Does this guy support PIM sparse mode? Does he have auto RP? And what scale can it do, right? Okay. As I told you, I am a catalyst-biased person, and I could spend a whole time telling you about this. That's not really the point of the session. The reason I put it in here was to show you that the Catalyst portfolio is set up in the same way to address the questions we've been talking about, right? We generically divide it into Axis and Core. Core also kind of covers the distribution. But the things we've been talking about, like, it should start coming to you really quickly, like, okay, it seems like the access is being a bunch of copper switches, RJ45 copper, because that's what's actually going to connect out to the IP phones and surveillance cameras, wireless access points, power over Ethernet, et cetera, right? I may have a modular philosophy, I may have a fixed philosophy, and we have options for all of those. And it also is a scale of devices, okay? And then same thing on the core, right? Tends to be fiber focused, so you'll see SFP fiber options, and then you'll see QSFP fiber options, and the same sort of modular or fixed scale. And then we just, the new part, we just introduced this X series. It doesn't really mean anything. We like to joke that it means I'm expanding or something, it's extra. These are just newer versions, so they have a more modern ASIC with much higher scale of number of entries and higher bandwidth, right? So it just adds to that same sort of increasing scale. In other words, if you're trying to choose between the 9300 and the 9300X, it's about scale, okay? How many ports do I have? What are the speed of my ports? How many MAC addresses? And so on, okay? Okay, as I promised, we would kind of go through each one of these. And so starting with the campus core, you'll notice in small letters it says baseline. So that's what I mean, like a generic, very, very simple core, right? It's the most basic of cores. And then we'll talk about variations of this, right? Okay, now I have this idea of an interconnect, and there's different words. When you get to the slides, I'll show you. And then other variations like this campus core and WAN edge. Now, to me, like I said, we'll spend most of our time here, and I think these are the most interesting slides. You will probably forget parts of it. I tried to use the big, loud yellow to catch your attention. And all the slides after this repeat this pattern. So as long as you understand what this slide is trying to tell you, you will recognize it on the next slide, right? At the very top, in green, tends to be sort of a external gateway protocol, probably multi-protocol BGP, doesn't have to be. But that's because he's connecting to other areas, right? The red is some kind of a interior gateway protocol, right? So it's your OSPF, your EIGRP, ISIS, that sort of thing, right? And then the blue is some sort of layer 2 environment, probably spanning tree, rep, those sort of things, right? So the colors in these drawings mean something, and this is a classic 3-tier design. So the first thing I talk about is kind of what is it even trying to do? The core pin, particularly in a 3-tier, his job is just a connection. He is a dumb layer 3 cross connect. That's his goal, right? I have a lot of distribution layers. This is fanning out to all these access layer switches. His job is just to get packets from point A to point B, okay? So your main focus now is basic routing and port density, right? The other thing I try to describe, and you'll see this on every slide, is kind of what is his uplinks or north side interfaces, and then what are his downlinks, his south side interfaces, protocols, and kind of wrap it up with scale. Like what kind of features tend to be in this role, and what kind of scale does this get me to, right? So this is your generic layer 3. Like I said, it's basic L3 routing packet forwarder, okay? And a cool little animation. Come on, okay. Now, an interconnect is just like it sounds. What's important here is it's a 4th layer. So the way this drawing has changed is that same 3-tier is now down at the bottom, one level. If my company is large enough, I may actually have multiple core distribution access areas, and I need to interconnect these, right? The other thing I meant to say is I also try to give alternate names to them. Sometimes we use different words for these things. So sometimes we'll use words like backbone, supercore. If I'm connecting to a data center, you'll hear DCI, but the concept is the same, right? What I've done now is I've introduced a new layer mostly for port density, right? It doesn't make sense to try and like have this enormous box and then try to perfectly interconnect everything, right? What I can do is I can put in a new layer, he then interconnects the different cores, simple, right? But in the one I'm using here, basically everything is the same. I've just introduced a new layer, and I've moved some of the complexity onto this new layer, right? And the cool animation. I gotta even remind myself that there's a cool little animation there. Okay, compare it with this one. I'll do the animation now. What we call the edge, okay? You probably get it by now. It's the exact same picture, but now he has changed significantly. He went from a very basic interconnect, it's just another L3 dumb packet core, right? Now you're starting to add a lot of different features, and that's what this edge is. It's the edge of the service provider, it is the edge of your private WAN, it could be the data center, et cetera, a DR interconnect, these sort of things. And you also probably notice the pretty rainbow colors. This is talking about inter-VRF routing, right? Typically, this is where we run things like MPLS and various different services. But because I'm now trying to interconnect these different branch offices and my headquarters, departments, I want to place them into different VRFs, right? Who cares? Why does that matter? Now I'm really taking some heavy routing, right? What a basic interconnect was just doing some basic OSPF, maybe a little BGP, few tens of thousands. Now you're getting into hundreds of thousands of routes. You need to like periodically go through a firewall, or you need to do VRF leaking, these types of things. How many VRFs can I support? And these questions, right? So again, the whole goal here is to tell you which box you're gonna choose, right? If your goal is a basic interconnect, almost any box can do it, right? I'm actually gonna build this now edge layer. I need to choose a box that has very rich features and very high scale, okay? You know, again, the subtle details in here, I'm not religious about the particular technology. We are going to talk about a few of these technologies. But there's a variety of these inter-VRF, you know, VPN type of services that are available out there. And again, when you're looking at the data sheets, this is what you're looking for in keywords. Do you support MPLS? Okay, how much MPLS? How many MPLS labels do you support? And so on, okay? The other thing is down at the bottom. In the other ones, I sort of went through it fast because they're dumb packet forwarders. So you probably don't have a lot of complex access control lists. You probably don't have a lot of complex quality of service, policy-based routing, NAT, these kind of things. But in an edge role, because he's connecting to everybody else, suddenly I need to turn on all this security. I need to turn on this really complex hierarchical QoS. So these are other little keywords when you're looking at the data sheet to keep an eye out for. And that's core. That's kind of the point, is like, let's get back to basics. Let's really just talk about what each one of these guys are trying to do and how does it affect my design. So now let's look at distribution. Same thing, there's a generic distribution, a baseline. We talked briefly about collapsed core. On my list, I put distribution with extended access, and then I mentioned earlier that I had to hide some slides for time. So this last one is actually one of the hidden slides. But I think by this point you get it. I'm just telling you about variations. It could also turn out that I now have this massive access layer beneath me. So I need to have all the MAC addresses beneath this massive extended access that comes up to the distribution layer, okay? So the distribution, in many ways, is the most complicated. I talked about the alternate names. It sometimes gets called a collapsed core. Another interesting name, aggregation. Who here prefers to call this layer the aggregation? Okay. So, funny story, this is about flow and traffic direction, okay? The direction of the traffic flow. So if you think about the words, to aggregate means to take many things and bring it into one, right? To distribute is to take one and distribute it out to other things. So if you think about traffic flow, most of the applications are coming from the data center, and then they're being distributed to the users in the access. So that's a clue who thinks like a data center person and who thinks like a campus person. It's a distribution, okay? But it's the box in the middle. That's what we'll call it, okay? Like I've said before, its main job is just to connect all those access layers, right? So in the generic baseline distribution, it can just be very simple. I'm not doing anything, the access layer is doing all the hard work. I just need to sort of connect these two layers. At the same time, and I've sort of been skipping over the north and the south. This is where that north and south matters. So on the south side, he's speaking to the access layer, and he's probably doing spanning tree, lots of spanning tree, number of VLANs, .1Q trunks. Then he has VLAN interfaces, SVIs, right? So again, looking at data sheets, how many SVIs do you support? HSRP, VRRP, how many HSRP groups do you support? These kind of questions, right? And then northbound, then it's probably just a simple IGP, probably speaks OSPF or something like that, and it's just the routes from this access layer beneath him. So all the VLANs he's responsible for will become routes that I advertise into that routing protocol, okay? So it tends to be in that medium area, right? But it's a mix of layer 2 and layer 3, right? And that's important when you get to the next one, because now I'm flattening that. So this was the reason I was making that statement earlier. Look, it's fine. If you want to flatten your network and you don't have a lot of MAC addresses, you don't have a lot of routes, it's actually perfectly fine. Conversely, if the boss is cheap, and I know I actually do have a lot of MAC addresses and I do have a lot of routes, maybe you do not want to collapse this layer. You should probably break it into a 3-tier again, okay? But the general rules are the same. If it's also operating as a core, now I have a much higher routing scale on this layer, okay? And like I said, there's actually a third, which is dealing with the access layer, but it's the same rule. By now, you're probably getting it, right? Okay, these are some basic rules, and once you understand the rules, you just keep repeating the rules, okay? Which gets us to access, generic access. So again, this is probably the most important area because this is what actually touches the endpoint, the human, the device that the human is using. This is where you tend to see your power over Ethernet. Most traditional designs do tend to be layer 2. Does anybody have a layer 3 routed access? 1, 2, 3, 4? Okay, 5. So it just proves my point. In fact, as a network designer, I encourage layer 3 routed access. Layer 3 is vastly superior to L2, but the fact is traditional designs are layer 2, and I can go on a side topic about that. It's about the behavior of the applications and the endpoints. So it's very natural to set up VLANs. It's a LAN, it's a broadcast domain. It's just so much easier to put a VLAN, and then I can do roaming, right? If the same application needs to work between buildings, that basically means set up VLAN trunks between buildings so that my users can roam between the buildings. That's why we do it, not because we like spanning tree, right? And for that reason, then it becomes about spanning tree. Again, like how many spanning tree instances do you have? How many VLANs do you have? And then how many MAC addresses does this one switch need to process? What happens when a topology change happens? How quickly can I relearn the size of that MAC address table? Okay? I've intentionally sort of, I haven't made a point about it, but in each one of the drawings, I was showing you kind of a modular view and also a fixed switch view of it, right? Same thing I said earlier, it's sort of philosophical. I'm not making any judgments, but there's, if you want to catch me offline, we can talk about the pros and cons of particular network layer design at a physical level and why, high availability. So my point is, like, there's a bunch of other reasons why you might choose one switch or another. And then I talked about this extended access. Same rules. By now, you're starting to get it. Here, it's a scale at that access layer. It's also new protocols like REP. It's a ring-based layer 2 loop prevention protocol. Very common in industrial Ethernet, any large designs. Now that so-called access switch is actually behaving like a distribution switch. All my trunks come up to there. He's now dealing with convergence of the network. So that cheap box that I probably would have put into a basic access may not be the best choice for this extended access design, okay? And of course, the cool little animation that I keep forgetting about. Okay, so now you guys know core, distribution access. There are variations like a core plus edge, a 4th tier. And there's combinations like an extended access, right? 4-tier design. And you can squeeze all of that into a 1-tier or 2-tier design. It's really just about scale, okay? So this part's really the connecting these guys together. I hope everybody knows what equal cost multipath is. And I'm using this term generically. Okay, this is actually a layer 3 routing term, but I'm using it to talk about all of the paths are equal. So even in spanning tree, it will then calculate the path cost of those layer 2 links, and that's how it figures out loop prevention, right? And then you can do load balancing based on that. So really, when I'm using ECMP, I just mean a bunch of links in a local area network that have equal cost, okay? And then compare that design, with the equal cost multipath is a normal, traditional design, compare that design with a virtual stacking design. And again, just pros and cons. Both of them are fine, it just depends on what you want to do. And by this point, I'm trying to like speed it up, so you guys, we're using the basic fundamentals we've talked about and then just sticking to the basics here. And it's a decision. You're making a design choice at this point. The first one's super basic. As I was explaining ECMP, you kind of get it. It just means I have redundant links, right? Whether that's spanning tree, whether that's a layer 3 routing protocol. We will do, what's important here is many different neighbors. I see each neighbor independently, right? So my path decision will be based on the number of neighbors I have and then the number of links that I have. So I'm like, okay, I've got 2 paths or I have 4 paths, and convergence and load balancing. So the part to remember of this slide is this protocol-based load balancing. There's another interesting note I put in here about tuning. Who here has done like asymmetric routing, had to tune, anybody had to like program, asymmetric routing means it goes up one way and comes down the other way. And it may not always do what you think it's supposed to do. The other question was like changing the timers. So you have to like be very careful about adjusting the timers so that when a link fails, the protocol will decide when to switch over to that other link. So it's a small note, but it's actually an important note in this decision-making process, right? Very stable. If you tune it correctly, it's amazing. Just make sure you understand how timers work and how it's going to affect network convergence, okay? And then how does that compare to the next one? It's the same picture. What I've done is I've introduced multiple links. I'm now doing them as a channel, so it's still technically equal cost multipath. But from a link level perspective, if one of them dies, it's actually the ether channel that's making that decision. So in the first one, if you talk about like OSPF timers, I should have picked an example. You can set it to about 1 second, right? It's a 3-second hold down. Guess what? You converge in 3 seconds. That's what I was asking about, like who's had to play with timers. There are things like bidirectional forwarding detection. You can get it lower than that. But the principle is that the protocol is making that decision. Ether channel itself, the channel has not gone down. It just lost part of its links. And so the topology stays the same. It's just going to move the load over to the other links in the ether channel. So it's on the order of milliseconds, right? And you haven't changed OSPF. OSPF never reconverged because the topology is the same, right? So yes, it's the same drawing, but that's my point, is like, yes, there are fundamental design differences by this choice, okay? And then last but not least, you guys are probably already ahead of me by now. When we talk about stacking or clustering, virtual switches, these are just words. The important thing is that I'm making them behave as one at an infrastructure level, okay? So instead of two different neighbors, they become one. And where I used to have equal cost multipath, right, and I would have neighbor number one, this is my adjacency, neighbor number two, this is adjacency, and then the protocol has to decide, oh, this link's dead, switch over to this one, right? Now that they've become one, guess what? I just have one neighbor. So suddenly my topology table becomes much less, and because it's using that same ether channel technology, it's immediately going to switch over in milliseconds, okay? So again, at a basic level, that's the design level thinking of what you're trying to do. There's no religion here. You can build a normal ECMP network, and if you do it right, it is stable and very predictable, okay? But there are also reasons why using a stacking design will simplify your network. Okay. You guys have already seen these kind of slides, so I'll just kind of go through them pretty quickly. And by the way, I just focus on the stack-wise because I hope you guys already know equal cost multipath by now. Here, when I was talking about making them one, this is very similar to when you have redundant controllers, whatever word you want. We call them supervisors, but the thing that makes the decisions, you can have redundant controllers in the system, and if the so-called active, the primary one dies, everything is synchronized to the standby, right, to the secondary. And by synchronized, I mean your MAC address table, your routing table. So as soon as he dies, he just immediately keeps forwarding. So the secret of stacking is that same, what we call stateful switchover, SSO. I've synchronized my MAC addresses, I've synchronized my routes, so that even if that entire switch dies, the other switch has an exact duplicate and continues forwarding. And the only thing that's changed is the ether channel, right? That's the whole magic of this slide, okay? And that was told from the core and distribution layer perspective. They tend to be done in pairs. Does anybody have more than two, like at each layer? I'm curious. You do? Tend to be like 4 or? Let me put it in a different way. Like, do you deploy them in blocks of 2? And you may have multiples of these blocks of 2. Okay, yeah. So that's why kind of the stack-wise virtual tends to be in blocks of 2. You might have multiple of these, but they still are like individual blocks of 2. But then there's a similar technology, the access layer. Most of you have probably seen or heard about this, but these are individual fixed switches with a stacking cable on the back, okay? All I'm trying to teach you is the same principles. In that stack, one of them will be elected as the active, and one of them will be elected as the standby, and they are then SSO synchronized. So even though there may be 4 or 8 physical switches, they appear as one, right? But it goes back to the basic principles we were talking about. How big is your routing table? How big is your MAC address table? Because all of that's going to be on that active switch, okay? All right, so up to this point, we've talked about, why do I have these places in the network? What roles are they going to do? We just got done talking about equal cost multipath versus stacking and ether channel. So now it's sort of protocol time. And again, I'm skipping over the basic L2, L3, because we've talked about it. Traditionally, that means some kind of a routing protocol, some sort of a spanning tree. So what about these new things Cisco keeps throwing at me, right? MPLS is not new, by the way. But at least EVPN and software-defined access, and it's set up in that same kind of way. Like, if I have these 3 options in front of me, how do I choose which of these 3 options makes more sense from my design, okay? So MPLS is not new. This was invented in the 90s, back in the 1900s. and it stands for multi-protocol label switching. So, also, by the way, I'm a big believer in the acronyms and like explaining what the acronyms. We just use the letters and we never actually think about what that is saying to me. It can be used by multiple protocols using a label, and a label just means an object or an IP to object mapping. Switching, multi-protocol label switching. So when they first came out with it, we had routing. Yes, it was the 1900s, but even back in the 90s, we knew how to route stuff. So when MPLS first came out, it was called tag switching. And the point was, switching's amazing. It's really fast, low latency, and then I can, separate things. But I have a routed core. Why do I do this? So whether it's a service provider or whether it's a campus network, I wanted a way to get switching into my layer 3 core. That was the birth of MPLS. Furthermore, then I started realizing, look, I can start to put these into different routing domains, and we created this virtual routing and forwarding. Again, like the acronym, we say VRF, virtual routing and forwarding instance. So just like you have a VLAN, I can put a completely different routing table in each one of these, and they don't talk to each other by nature. I can keep them separated. So that was the birth of MPLS. Is anyone using MPLS in the campus today? Quite a lot of you. Okay, well, you already know what I'm talking about. Anyone that didn't raise their hand, the reason I included it is the reason everybody just raised their hand. MPLS has not gone away. And even myself, to this day, get asked, like, do you run MPLS in the campus? Yes, absolutely we run MPLS in the campus. And it's probably to accomplish these goals. I want to get the benefits of switching, I want to do it based on labels, and I want to enable these VRF services. That's why I'm doing it, okay? So as you're reading it, that's what I'm trying to highlight. I can get, and I also use these terms, you'll hear this with the people talking about fabric, they'll say underlay and overlay. So the underlay is your basic routing. It's getting it from point A to point B, okay? Or the transport layer. But it's dumb. It is intentionally dumb. Put it a different way. It is simple. I just need to get it from point A to point B. Keep it simple. Keep it simple, stupid. On the other hand, my business is requiring me to give services, and I need to make sure this department doesn't talk to this department, or these IoT boxes don't talk to the, printer or something. So you put that in the so-called overlay. So you have under and over. I know it's remedial, I'm just making a point. But all the magic, all the so-called services happen in the overlay. So if you think about security, think about quality of service, policy-based routing, it's all happening in the overlay. And the underlay is just simple, okay? So, like I was talking about, that's what you'll see in each one of these. All three of these accomplish the same goal. Keep it a simple underlay and enable some kind of services in the so-called overlay. And I'll add one more point. Overlay is another way of saying a tunnel or an encapsulation, right? So other examples are like GRE, wireless CapWap, right? All we're doing is we're putting an additional header on the front of it, and I don't care what's inside anymore. I'm just going to make my forwarding decisions and my security decisions on this outside encapsulation, okay? So that's kind of now where the decision points come in. MPLS was built in a time it gave me VRFs, right? It gave me all the cool fast switching of labels, but it's just layer 3, right? I could also add in technologies like EOMPLS and VPLS to get layer 2 VPN, but I'm still not really doing any complex layer 2 security capabilities, okay? Now, meanwhile, as the new technologies have evolved, we came out with software-defined access. Anybody looking into software-defined access? Fair number of you? Okay, there are entire sessions, again, on SD-Access. This is not the SD-Access session. But it is a Lisp-based control plane with a VXLAN encapsulation, okay? So inside of that VXLAN encapsulation is what's called a virtual network, but it's a VRF. So I can do layer 3 segments. I can start to put people into different routing tables. One of the things that's new is it's called VXLAN GPO, Group Policy Option, or otherwise known as group-based policies, right? So in addition to a VRF, I can also take a group tag. Okay, so when people are talking about SGT, what they're really talking about is this tag in the VXLAN header. And when they're talking about this amazing group-based policy, what they mean is I'm taking that tag and I'm using that to build my access list and my quality of service, okay? So when you're making your decisions between MPLS, EVPN, and SD access, the key thing to catch there is, and I put it down here, L2, L3 VNIs and SGT segments. Other words you will hear are like macro segmentation and micro segmentation. By the way, I don't like fancy words. Macro being big, that means VRFs. Micro means SGTs. Okay? Now, BGP EVPN. Who here is using BGP EVPN or looking to deploy it? Okay. Again, no religions here. So one of the main things with BGP EVPN, it's an address family within EVPN. Did I say that right? It is an address family within BGP to do Ethernet virtual private networks. And the keyword there is Ethernet, right? So giving L2 environments inside of the BGP routing protocol and sharing the MAC addresses with that, okay? I won't belabor the point. But it is also using VXLAN encapsulation, right? So, and I'm only going to address standards-based EVPN, by the way. So if you are using standards-based EVPN with standards-based VXLAN, then what you get out of it is layer 2 and layer 3 virtual networks, which is another way to say VRFs, okay? So those are your 3 decision points. MPLS, it's old, but it is very stable, well-known. It's really more L3 VPN. I can add EOMPLS VPLS for L2 capabilities, but now I kind of have to maintain both. EVPN, its main benefit is I actually get L2 and L3 natively in a single routing protocol, BGP, right? But I don't have any of this micro segmentation stuff, okay? Talk about SD access, I get the L2 and L3 VNIs, and I can add this SGT micro segmentation into the encapsulation, okay? That's your basic decision points there. All right. These ones I'm going to flash through. I'm looking at the clock telling me that I'm running out of time. But the important thing is what we talked about, the so-called underlay. So in other words, I'm going to enable some kind of a routing protocol between all the different layers. And very briefly, I talked about a layer 3 routed access. So one thing that is implied here is that that device, wherever the encapsulation starts, is routed. So one of the interesting design decisions is, you know, is my access layer ready to support layer 3 routing, okay? That 9300 you got can support layer 3 routing. And then as I mentioned, the things like the VXLAN, and then if you look at the features, because it is not using any SGTs or any group tag, you're going to do traditional IP-based access lists, okay? And then I show border versus leaf. Those are 2 sides of the tunnel, 2 sides of the encapsulation. Send it from the leaf to the border, okay? So the leaf is just the other side of that. And same thing on SD access. I said it is also using VXLAN encapsulation, right? So you'll have this border, same thing as EVPN border. They don't call them leafs, they call them edges, but it means the same thing. So your core is traditionally your border because it's about to leave the network, and then your access layer is an edge. But the important thing there on the slide is this VXLAN GPO. So that's group policy option. He's carrying that SGT in the VXLAN frame, okay? All right, wireless and security. Like I said, just a few of these. I'll be quick because now you have a sense of all these different layers of the network. One of the interesting things about wireless, and I actually touched it a moment ago, is it is a tunnel. It runs on CAPWAP, which is control and provisioning of wireless access points. What to remember is that means I tunnel all the way up to where the wireless LAN controller is. And this means the scale of the device connected to the wireless LAN controller needs to support all those MAC addresses and all those routes. Anybody doing centralized wireless for your company? I'm actually expecting almost the whole room to do it. Okay. It, like I said, just directly translates into MAC addresses and things like ARP and neighbor discovery. That switch needs to have a massive MAC address table and a massive ARP table. Okay. And then firewalls, ACLs, this is more about how I'm connecting to that firewall. Am I doing it as a layer 2 firewall? Am I doing it as a layer 3 firewall? Are there VRFs? These kind of things, right? So you need to talk to your security operations person. What is this firewall thing I'm connecting to? Because that's going to affect how I choose my switch or router connected to that firewall, okay? Then a recap, we're finally at the end. Remember those pins, okay? Just in your head, think about what each layer does. Why do I scale it that way? And it'll actually make your life easy. Keep learning. This is just the fundamentals. We also have these things called Cisco validated designs, which go very, very deep on specific design topologies, okay? And WebEx session, I think you see this in all the sessions. Feel free to reach in there and ask questions if you think of some more later. And thank you guys so much for coming to the session.